Welcome to This Explainer. I'm absolutely thrilled you're here today because we're going to build a really powerful, flexible mental framework for solving complex calculus area problems. We aren't just going to sit here and memorize formulas. We're going to fundamentally understand how to measure space in a way that will completely change how you view shapes on a graph. Okay, let's dive into this. Here is our roadmap for today. 1. The area between curves. 2. Finding your boundaries. 3. When curves cross paths. 4. Sideways, integrating along y. And 5. Beyond area, introducing volume. All right, let's start with section 1, the area between curves, stretching the rectangle. Let's just ground ourselves for a second. Remember, the best math explainers always build on what you already know. You already know that a basic integral finds the area under a single curve, right? And it does this using vertical Riemann rectangles. It's basically partitioning an interval to approximate area using a series of rectangles, eventually taking the limit to infinity. We pack a bunch of these rectangles under a curve, add up their areas, and as that number approaches infinity, boom, exact area. That vertical rectangle, that's our ultimate measuring stick. Now, what's really interesting about this is how we just level up that basic concept. The area of the shaded region is the top curve, f of x, minus the bottom curve, g of x. Instead of finding the area all the way down to the x-axis, we literally just stretch our vertical measuring stick so it spans the gap. We span the gap between the top curve, our f of x equals x plus 4, and the bottom curve, g of x equals 3 minus x over 2. The height of our rectangle is just that difference. We integrate it, and there you have it, the exact area between the two curves. Moving right along to section 2, finding your boundaries, setting the limits. So here's the thing. What happens when the problem doesn't give us the starting and ending interval points? The training wheels come off. How do we integrate if we don't actually know where our compound shape begins and ends? Take a look at the region bounded by f of x equals 9 minus x over 2 squared and g of x equals 6 minus x. We've got this downward-facing parabola and a straight line just slicing right through it. The shaded region is totally locked in there between them, but notice how the graph doesn't just hand us our A and B starting points. We actually have to find those intersections ourselves to know where to start and stop our integral. To pull this off, just set f of x equal to g of x and solve for x to find your limits of integration, A and B. We need to figure out exactly where these two functions share the exact same values. In the scenario we just looked at, doing this quick bit of algebra tells us our curves intersect at x equals -2 and x equals 6. You absolutely want to lock this rule into your toolkit. Do this algebraic step first always to find your true boundaries before you even try to set up that integral. Let's jump into section 3, when curves cross paths, navigating intersections. Now we're getting into the really fun stuff. We know the whole top curve minus bottom curve drill. But what happens if our curves cross paths halfway through our region? This is a classic exam trap. If you've ever felt the absolute frustration of setting up a massive integral perfectly, only to get a negative area at the end, yeah, this is exactly why it happens. You can't just blindly apply the formula without understanding the graph. And this brilliantly illustrates exactly what I mean. We're looking at R1 and R2 subregions bounded by f of x equals sine x and g of x equals cosine x. From 0 to pi, they bound two distinct regions. Notice how in that first part, R1, the cosine curve is on top, but then right at pi over 4, they intersect. Suddenly, in R2, the sine curve is on top. They literally take turns. Because of this swap, we absolutely cannot use a single integral. We have to split the integral right at that intersection, pi over 4, and physically swap our formula for the second part, so we are always subtracting the bottom from the top. Which brings us to section 4, sideways, integrating along y, the paradigm shift. This is a total perspective shift. We have a region requiring two complex x-axis integrals versus the same region simplified with a horizontal rectangle. In the first scenario, if we use vertical rectangles along the x-axis, the top curve actually changes partway through. We'd have to split it into two messy, separate integrals. But if we just tilt our heads, take our rectangle, and lay it horizontally, the problem becomes beautifully simple. Slicing horizontally along the y-axis means the right curve and the left curve never change, just one elegant integral. So we're looking at an x-axis integral, which is top curve minus bottom curve with a dx thickness, versus a y-axis integral, which is right curve minus left curve with a dy thickness. Instead of everything being a function of x, everything becomes a function of y. Our whole symmetrical framework shifts to right minus left. It is the exact same logic we've been using, just rotated 90 degrees. So the crucial point is this actionable 4-step workflow. Number 1, graph the curves. Always do this so you can visually see what's on top or on the right. Number 2, find your intersections algebraically so you know your exact boundaries. Number 3, strategically decide if vertical dx rectangles or horizontal dy rectangles make the math cleaner. And number 4, integrate. Stick to this workflow and you'll absolutely crush these problems. And finally, Section 5, Beyond Area, introducing Volume 3, The Next Dimension. Let's move on and see how this builds, because this is where the whole journey is headed next. Here we have a 3D solid generated by translating a plane region along an axis. You see, the area we've been finding this whole time, it's really just a flat cross-section. If we know how to find the 2D area of that flat face using the integrals we just learned, finding the 3D volume is literally just a matter of multiplying that cross-sectional area by the height of the shape along an axis. I really love this quote. Just as area is the numerical measure of a 2-dimensional region, volume is the numerical measure of a 3-dimensional solid. It just clicks, right? Calculus isn't some random bunch of disconnected rules. It's this beautiful, escalating series of logical, geometrical extensions. We stretch a point into a line into an area, and an area into a solid. Which leaves us with this final thought. If a 2D integral can take an infinitely thin line and stretch it into a measurable area, what kind of mind-bending shapes can we measure when we stack those areas into the 3rd dimension? That is the absolute magic of the slicing method and solids of revolution, and it's exactly what you're ready to tackle next. Keep that mental framework strong, and I'll catch you in the next explainer.